In this video for 2.7, we're going to look at polynomial and rational inequalities. So you might recall that I'm assuming you guys have looked at linear inequalities. So you would plot the line, you would decide whether the line was included, and then you would pick all of the area above the line or everything below the line. In this instance, or at least for polynomial inequalities, we are looking at the parabola or the cubic function or whatever it is that we have. And we're trying to determine the regions for which the function is either above 0 or below 0. So you'll see here that there's four forms. It can be less than 0, right? Negative, below the x-axis. Greater than 0, above the x-axis. Less than or equal to 0, which would include points on the axis and below. And then greater than or equal to 0, which would include points on the axis and above. So let's see what our steps would be. The procedure for solving polynomial inequalities is first to, even if it's less than and equal to just take the form and express with equals 0. Let's worry about solving it that way. Find the boundary points, which are basically the zeros, right? If that's where the function's equal to 0, we know that's the x-intercepts or the zeros. Create a number line using those boundaries to divide the number line into intervals. Again, I keep saying this, and you're probably getting tired of it, but it's important. When you get to calculus, you'll be doing something very similar to this, talking about whether functions are increasing or decreasing between particular points. So what we do here, and you'll do in calculus, is because the boundary values or the boundary points break up the number line into an interval, you're going to take test points or test values, which are values that lie in between the intervals, and test each one of those within the function. If the function is positive, then for all numbers x that are in that interval, the function is positive. If you get negative for the particular value that you plug in, then the function is negative for all values x in that interval. The final part is to write the solution set, which is really just going to be in interval notation. All right, so let's take a look at an example here. And by the way, if you're looking at the picture, notice that this inequality says x squared minus 7x plus 10 is greater than 0. Well, that's expressed by the blue parts of the curve. Those are all points on the curve that are above the axis. The points that touch the axis are not included here because it's not equal to. Same goes for this bottom part in red. Right, this says less than 0, so the solution set is everything below the axis, also excluding the 2 points on the axis. So our first example is less than or equal to. Let's see if we can figure this one out. So first thing we need to do is determine where is this thing equal to 0. So I'm just going to say, let's take the 2 factors, set them to 0, and forget about the inequality for just a second. And if you think back to when you did this with linear functions, you did the exact same thing. So I need to solve each one of these. So x plus 2 gives me x equals negative 2, and x minus 3 gives me x equals 3. Those are my 2 roots. And in this case, they are the values that are my boundaries. So the second step is to create a number line. This number line is broken up with negative 2 and 3. I always put 0 on my number line. And then what I like to do is to tell me where my boundaries are, I draw arrows. So this is a boundary, this is a boundary. Now you'll notice I had 2 boundaries, right? And how many intervals? Well, I have 1, 2, 3. So you always have one more interval than you do boundaries. Okay? If that's the case, if I have 3 boundaries, I need to find 3 test points to plug into the function and see if it makes the inequality true. So let's make a little table here. Let's start off with the test point. Okay. Or if you prefer, you can do a quantity over here. That is the interval that you're taking the test point from. So the first interval is from negative infinity all the way up to -2. Okay, so negative infinity up to -2. And because this inequality is equal to, we can say equals. All right. Then the second interval is from -2 to 3. Again, I am including those, so I'm using my brackets. And my third is from 3 to infinity. Now we need to establish a test point. So our test points just have to be within the interval. They can literally be any number you choose. So to the left of -2, I'm going to choose -3. That's the next integer, and it's so integers are easy to work with, right? And it's negative, so it puts us in that area. I'm going to choose 0 in between -2 and 3. You could choose -1, 0, 1, 2, 2.63, whatever number fancies you, you can use it as long as it falls in that interval. I'm going to pick 0 because it's nice and easy to work with. And same thing on the other side. Within this interval, I'm going to choose 4 because that's another integer that we can very easily plug into the function. So here, we're going to actually plug it into the function and see what we get. And then here, let's say included or not included, right? So included question mark. So it's included if this statement is true. All right. So let's plug -3 in. So we'd have -3 plus 2, and then -3 minus 3. -3 plus 2 is -1. -3 minus another -3 is -6. Negative times negative is positive. So we end up getting 6 is less than or equal to 0. That is not true, right? And because of that, this is not included. All right, try our test value 0. So we plug that in. 0 plus 2 times 0 minus 3 less than or equal to 0. 0 plus 2 is 2. 0 minus 3 is -3. That is -6 less than or equal to 0. That is true. So we do include this section. The last one was 4. So I'm going to plug that in. 4 plus 2, 4 minus 3, less than or equal to 0. 4 plus 2 is 6. 4 minus 3 is 1. We get 6 again, which is not true. And therefore, we do not include this section. So the solution set is only from -2 to 3. And again, we are including those because the inequality was less than or equal to. Okay. Now, let's look at the plot of this guy and determine which part of the plot corresponds with -2 to 3. So let's go to Desmos. I've already plotted this guy here. So this is the function. Here are the points where it crosses the axis. We saw 4, -2, 0, and 3, 0. And you'll notice between those two values, that part of the function is below the x-axis, which is less than or equal to 0. So that would be our solution set, just this portion below the axis. For example B, there's a little bit of difference here, right? We have to do a little bit of manipulation, but the first step is to get the inequality greater than or equal to, greater than 0 in this case. And then we're going to treat it with just an equal sign. So to get that 15 to the other side, I just have to subtract 15. from both sides, and I end up with this inequality. Once I have this inequality, I don't really care about the inequality right now. I'm just going to say this. My job at this point is to factor. You could use the quadratic formula if you prefer. So I'm going to do our grouping method. I take the 2 and multiply by -15. So I need two numbers that multiply to -30 and add to 1. So let's think of factors of 30. I believe we could use 5 and 6 as long as the 5 is negative. So I will replace the x in the middle with a combination of those two. So I bring down the 2x squared, I bring down the -15, and I plug in a +6x and a -5x. Now I need to group. So I have 2x squared plus 6x. And I always suggest if there's a minus to do plus and stuff the minus inside. Okay. Now, what do these first two have in common? Well, they both have a factor of 2 and they both have a factor of x. So let's take out a 2x. What's left behind would be x plus 3. So we're expecting what we get out of this one to look like x plus 3. These two here have a -5 in common, so I'll take that out. That leaves me with x plus 3. So my two factors are what's inside the parentheses, x plus 3, and what's outside, which is 2x minus 5. I then need to solve, excuse me, each one of these equal to 0 to get my boundary points or boundary values. So here I'm going to add 5 to both sides and divide by 2. And I get x equals 5/2. So my two values are -3 and 5/2. So I would draw my number line. I'm always going to just put 0 here just to keep my bearings. I have -3, and then I have 5/2. Okay. Again, -3 and 5/2 are the boundaries. So I'm going to put arrows there. Once again, we have two boundaries, therefore we're going to have 3 intervals. Those intervals are, and again, keep in mind, we are just greater than here, so we're not equal to the boundaries. So this interval is -∞ to -3. The interval in the middle is -3 to 5/2. And on this end, it's 5/2 to infinity. So now we need to pick our test points. Again, pick the easiest numbers you can think of. I'm going to do -4, 0, and 5/2, that's 2.5, so I'll pick 3 on this end. Then we want to set up our chart. So I'm going to go ahead and scroll down here so we have some more room. We have our interval. We have our test point. We have the actual function. So the function in factored form was 2x minus 5 times x plus 3. And that was greater than 0. And then the last part is, do we include, right? Okay. So the first interval was negative infinity to negative 3. The second was negative 3 to 5 halves. And the last interval then was 5 halves to infinity. And we chose the points negative 4, 0, and 3. All right. Again, you can pick any test point you like as long as it falls within this interval. So, for instance, I did 0. You could have done 2. You could have done negative 1.67932 if you wanted to. All right, I'm going to plug these in and see what we get. So I have 2 times a negative 4 minus 5 times negative 4 plus 3. 2 times negative 4 is negative 8. Negative 8 minus 5 more is going to be minus 13. Negative 4 plus 3 is going to be negative 1. Negative times negative is positive. So we get 13 is greater than 0. That is true, and therefore we include that interval. All right, let's try the next one. Let's plug in 0. 2 times 0 minus 5 times 0 plus 3. Okay. 2 times 0 is 0. So we just get negative 5. And then we get positive 3. That's going to give us negative 15, which is not, right, not greater than 0. And therefore we do not include that section. All right, the last section, we're now plugging in 3 for x. So we have 6 minus 5, which is just going to be 1. And then 3 plus 3, which is 6. And so that's going to give us 6 is greater than 0. That is true. And therefore we include this interval. Just move this down here slightly. So our solution set is the interval negative infinity to negative 3 union with 5 halves to infinity. Let's go ahead and take a look at the actual graph of the function. I've already taken the liberty of plotting it for us. So 2x squared plus x minus 15 looks like this. You'll notice the 2 points, negative 3 and 2.5, or 5 halves. And the question was, when is this thing greater than 0? Well, from negative 3 on, right? Or if you'd rather, negative infinity up to negative 3, not including that. And from 2.5 or 5 halves, not included, all the way to x equals infinity. This region down here, right, is less than 0, so it is not included.